Now we have talked about one converting waveforms into sequence of bits, both generating these bits via good source coding. And we have looked at the slightly unrelated topic of circle of ERE. Yeah, I was missing an S. R. Interpretation, geometrical interpretation of now. Let's start to make sense of these. So digital bits or zeros and ones are abstract ideas and cannot be transmitted over a. We have discussed this point slightly last semester, right?
Yes,
So
sir.
these zeros and ones are abstract ideas and cannot be transmitted over channel. So how did you do, or how did you work around this in the digital hardware lab? In digital hardware lab, you actually worked with digital logic,
Yes,
right?
sir.
So how did you work around this? How did you physically see bits?
Sir, we map them to voltages.
Yes, yes. So, however, these can be mapped to voltages, or these can be mapped to waveforms. So say if I want to send bit 0, I send cos. No, no, this also happens. Yeah. So suppose you want to transmit a message. You have you you guys know those mock lasers that sell for like 50 rupees a piece and can throw light at quite a significant distance.
Yes, sir.
LED
Yes,
based
sir.
lasers. Yeah. So
Yes.
suppose you have two of those, a red one and a green one, and you want to tell a friend who lives next door or in the next street that it's safe to come out. So you throw the red laser to his house when uh, it's safe for him to come. So tell him that, okay, I'll message you at 8 p.m. for 5 seconds. and I'll throw the light for throw the red light for 5 seconds if it's safe for you to come. I'll throw the green light for 5 seconds, or I'll throw the green light if it's safe for you to come. I'll throw the red light if it is not safe for you to come. Makes sense? This is a digital
Yes.
communication. You are uh, so zero is not safe to come and one is safe to come.
Yes, sir.
Yeah. So uh, this is digital. Is this digital communication? You are you sending the light.
Yes,
So
sir.
I sent cos 2 pi f0t. What is this? And how is this? Yeah. Cos 2 pi f0t. For why is this coming here? Yeah. For not 5 seconds. For t seconds. Sorry. Yeah. For t seconds and signal line. Right. For t seconds. If right. Makes sense.
Yes, sir.
Yes.
Yeah. Now suppose your friend is pretty sharp and my laptop says repairing disk errors. This might take over an hour to complete. So we are stuck without handwriting today. I'm sorry about that. My laptop. Ajay, can you please mute yourself? I'm hearing myself. Yeah. So yeah, I'm sorry about that. My laptop is misbehaving, but yeah, you cannot do anything about it. I started it. I switched it on at 2 p.m. and since then it has been. Yeah, Shubhashish, want to say something?
Sir, yes, sir. The second part, this 1, 2, 3 that you have stated, the second
Yeah.
is the DBCM, right?
Yes.
So then the what was the first part exactly?
Previous semester
Okay,
sampling
okay.
quantization.
Yes, sir. Yes, sir.
Fine. So yeah. So now let's assume that your friend is really sharp and he can read binary for that matter. So you can, you know, ASCII.
Yes,
Yes,
sir.
sir.
Yeah. So you can actually send him ASCII symbols. That is, you switch between red and green lights fast, and he can note those down, and he can decode an entire message out of that. Say red, green, 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 red, 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 red. That can be done. He can note down an entire message.
Yes,
Yes,
sir.
sir.
Yes. Great. So now let's so in that case, basically, if you transmit or switch these on and off. On every, say, t seconds, you are 1 bit every t seconds. Make sense? 1 bit every t seconds,
Yes, sir.
right?
Yes, sir.
Now, uh, assuming that your friend has, you have access to multiple such lasers, and your friend has the capability of recognizing all the colors. So let's say we have all the colors of the rainbow available with us in lasers. That can be possible.
Yes, sir.
So has anyone read Green Lantern comics?
Yes, sir. The
Yeah,
seven.
yeah, there are 7 emotional colors. So plus there is black and white. But let's
Yes.
say 000, when you want to transmit the sequence 000, uh, when you transmit nothing, for that corresponds to the sequence 000. Violet corresponds to blue. G. Yeah, I forgot G. So this is G, this is Y, this is O, and red 2. Don't throw infrared rays and set his house on fire. That is not allowed. So then you can actually, so now you are sending 3 bits every, right?
Yes, sir.
Yes, sir.
So you are sending 3 bits every t seconds. So the key takeaway is we can have symbols that can convey multiple bits per channel use. So basically the channel is the communication medium. So every time you use the laser or push on the laser, that is one channel use. So you can send multiple bits per channel use, and you can send a sequence of bits. So this is information transmission, and you can always get back the. Uh, so this has woken up again. Let me try to log in. Yeah, you can send a sequence of bits. So now we define two things. One, symbol rate or baud rate. The number symbols sent per second. Second thing is bit rate. Bits sent. You have, so these bit rates, unlike your friend who has to read these manually, you know that these bit rates and symbol rates can go into megabits per second easily. Or even in the case of physical uh, uh, wired LAN, these can easily go into gigabits per second. Right? So now, and this is basically what we are doing. This is an example of a digital modulation scheme called frequency shift keying. So basically what you are doing here is you are changing the frequency of the transmitted waveform in accordance with your symbol, right?
Yes, sir.
Yes, sir.
So since you are changing the frequency of the transmitted waveform in accordance with the transmitted symbol, this is a form of FM. This
Yes,
is a
sir.
form of FM. So
Mm.
this is basically an analog to FM or frequency modulation, and you are using the and you are actually modulating the carrier waveform such that you are able to send 3 bits every t seconds. Similarly, since we can do this via frequency modulation, we can also try to invoke other modulation schemes such as amplitude modulation and phase modulation, because phase modulation here is quite different from what we had for continuous wave modulation. Or rather, here phase modulation will play the key part, or phase modulation is the star of the game, unlike the continuous wave case. So now let the bits to be grouped into chunks of k bits. Fine. So we decide that we will send k bits at a time. Fine. We can send k bits at a time. So which means that there can be there can be m equals 2 to the power k possible symbols, right? Yeah, Shubhashish.
Sir, but here K bits, like in that example, we had to use a 7 different colors. But how
Yes.
exactly we can do? How can we do it with just two colors? For
So
example,
I
if
never
we
said that
only
we have two colors. Did I say that we have two colors?
no, sir.
Then I'm talking about a general case. Now this was a specific example.
Okay.
Now I'm talking about the general case. Let the so there can be, I've said this m equals 2 to the power k symbols,
Hmm.
right?
Yes.
So there are 2 to the power k symbols, right? And you can easily see that if the baud rate is RS, then the symbol rate becomes log 2 m. RS times log 2m, right?
Yes.
Also, let the mth symbol to be transmitted be represented by SM. Fine.
Sir, isn't baud rate and symbol rate same?
Yeah. Oh, sorry. Then the bit rate becomes. My bad. Yeah. Let the mth symbol waveform to be transmitted be represented by SMT. Fine. You transmit this waveform SMT for the mth symbol. And the energy needed for transmitting the is right. This is fine.
So
Yeah.
you said that log m base 2 is basically k, right? So it's
Yeah.
RS times k.
Yes.
Oh,
But we will be generally talking about the number of symbols rather than number of bits per chunk.
okay.
That's why I use this notation. Otherwise, that is K. You are right. So this and the energy expended for transmitting the mth symbol is ST mod, SMT mod, and you can then so the average energy required for this operation is, oh, sorry, this is SMT. Average equals by m some, right? This will be the average energy. One note is starting. You'll have to bear just another couple of minutes of this. So the average power This makes sense? The average power consumed?
Sir,
Uh,
it was epsilon average. This is
oh
E
yeah,
average.
this is also E. This is not epsilon. So see,
Okay, yeah. Good.
this is epsilon. This is small epsilon. Don't know whether, yeah. So this is capital epsilon, which looks slightly different from regular E. So there are different symbols. So we use E as symbol. So maybe another minute and we should be good to go. Yeah. So anyway, in general, the symbols T are bandpass signals. In general, these are bandpass signals. And can be modulated either linearly or non-linearly. So the meaning of linear and nonlinear modulation in this case will become clear eventually, but we will start with the we will start this discussion with simple linear modulation scheme known as amplitude this case the, wait a second, just a second. I'm doing something slightly wrong here. No, this is right. This is right. Yeah, in this case, yeah, now this is lecture 8. Yes. So in this case, the amplitude of the
So your screen is not visible.
oh, sorry, I tried switching to my laptop for a second, but that's not ready yet. Now is it visible?
Yes.
Yeah, so
So,
my laptop should be ready. Oh, so bad day. Yeah, anyway, I'll continue. So the amplitude of the symbol being transmitted depends on the bit sequence. For example, transmit. For example, 00 means -3, or rather, let me do it this way. So let the, for example, considering the symbol duration to be 0 to capital T seconds. If I want to transmit 0 0. Then I send -3 -3 cos c minus cos minus cos by for in general for right. I can do this.
Yes, sir.
Yes, sir.
Yes. So this is one symbol, and this is this is this is called by two names. One. So this scheme is called by two names. One, digital PM. PM, you know, pulse amplitude modulation. The second, amplitude shift. You can use either of these two names for this. So the textbook uses digital PAM for this scheme. In general, for digital PAM, yeah. In general, for digital PAM, SM equals, or rather SMT equals AM PT, where PT is the communicating pulse, and in this case, or in case of this example, PT equals cos.
Sir,
Yeah.
uh, sir, 0 0 has been donated -3 cos 2 pi FCT and 1 1 2 3 cos 2 pi FCT.
Yes.
So there has been a phase change of 180 degree.
Yes.
So can it be also the phase shift keying?
No. No.
Okay, but
That's why I've taken this specific example. Phase shift keying. Yes, we will come to it, but this is not phase shift keying, because here the main component that is varying is the amplitude.
okay. And but we are also doing two different using two different phases. No, that's why I was asking.
So positive amplitude and negative amplitude, yes. So we will your doubt will I'll become clear as we move forward. That's the only thing I can say. So yes, there is something called phase shift keying, and as I said earlier, that is quite important, but this is not phase shift keying. Phase shift keying is phase shift keying involves more phases in general. So you don't be happy. You aren't happy with just two phases in phase shift keying. Okay.
Okay. Okay, sir.
So 0 less than equal to t less than capital T. Uh, How do I? uh, Maybe this will help. Yeah, this helps. No, this doesn't help. Want to treat this entire cost thing as a single block. Maybe this will help. Yes. If I write the cost here, yes, x v, so 0 x 0. Fine. This control x and this gets here and this gets. So yeah, you get the idea, I believe. So now the laptop has gracefully turned or has been kind enough to turn on. Let me try one more time if this thing cooperates. Fine. So you can see the screen now.
Yes.
Yeah, so yes, I'll make this slightly bigger so that it's easier for you. So you can see the, yeah, now you can see the enlarged version and the keyboard has come. So, so for things like my laptop, if they misbehave, you know they are working properly. So yeah, anyway, so PT equals this. And in general, SMT for m equal to 1 to capital M can be seen as a set of signals over the basis PT, right?
Yes.
SMK can be seen like a basis. So now say this is the PT axis and so 0 0 0 1 1 0 1 1. Fine. I can draw these single signals like this. I can on the PT axis, if I denote PT as an axis, I can draw these signals like this.
Yes. Yes.
So you can say this is
Like that
S1T.
5D cannot be origin, right?
No, this is PT. Say
Yeah,
when you
is
draw
that
this
origin of that
x,
axis?
y, this is how you write. This is PT.
Yeah, yeah. Okay, okay.
Fine. So this is PT. So this S1T, S2T, S3T, S4T. In general, for PAM, SMT equals AMPT with AM equals 2M minus 1 minus capital M. Fine. So for M equal to 1, for small m equal to 1, this is 2 minus 1 minus capital M, or equal to minus M plus 1. And for M equal to small m equal to capital M, this equals M minus 1. Right? So this gives us, so you get all of these are odd numbers with no zero.
Yeah,
Yes,
2m
Fine.
sir.
minus 2 symbol.
Yes. So you will get M symbols in total with all of them being odd numbers and symmetric about the origin like this. So you can extend this indefinitely. So EM equals fine.
Yes,
This
sir.
is fine. And right.
Yeah,
1 square plus 3 square plus 5 square plus M minus 1 whole square. Right?
Yes, sir.
So now from what we have learned, so this is sum of squares of odd numbers. So so right, arithmetic progression. So this was a result in arithmetic progression, right? So sequences and series, class 11th.
Yes,
Yes,
sir.
sir.
Yeah. So
yes, sir.
this is I don't think I have to prove this. So fine. Also, we can write SMT equals real part of 2 SMLT e to power j 2 pi fct, right, equals real part of, oh, sorry, not 2, my bad. Yeah, real part of am sum gt j 2 pi fct. Fine, where gt is called the shaping pulse. GT is called the shaping pulse, and in this example and in general, GT equals, and unless specified, not in general. So the shape of this GT will be the point of contention in our next chapter.
Sir,
Just a second, let me write this.
okay.
Yes, shoot.
Said that EP that you introduced,
Yeah,
what was that EP actually? Like,
remove AM, whatever is left is EP. So the
yes,
power, the energy of in P.
okay.
Right. So AM square I move out. See, AM square is a constant. AM square I can move out of the integral.
Yes, sir.
So this and GT is this. So also considering the geometric form of PM again. So this is normalized with respect to, or rather, let's not talk about EG too much. SMT equals AM root over EP. Fine. We are talking about the passband signal. So again, S1, S2, S3, S4. This will be minus 3 root over EP, minus root over EP. Right? Agreed?
Yes, sir.
Yeah. So now you see that we when we draw this, we draw the points as we mark the points in a way, and this forms a shape. This forms a recognizable shape, right? I can do this in 2 dimensions as well.
Yeah.
Yeah, so this is phi t, this is important. So we show these symbols, or we show these signals as points in a 2D representation that seem to form a recognizable shape. So if anyone, so you guys, I believe you guys have stargazed at Lohit sometime. Have you ever seen this in the sky? It's quite clear from the campus at least.
Sir, is it Orion or
Yes. So anyone else? Has anyone seen this?
Yes, sir.
All those who have seen Orion, raise your hands. 2, 3, yeah, 4 people. Okay. So yeah, others, when you get back, please ensure that we have quite a nice camp. So hopefully we'll get back this year. Hopefully, I am not committing anything on behalf of anyone else. So hopefully, when you get back, we have a nice pollution-free campus. You should at least so, and this is one constellation that is visible. So this thing is called a constellation. So an arrangement that changes into a recognizable shape. So this form of representing the signals is also called a constellation. And the distance between 2 points in this constellation is also important. So this case dmn equals root over the 2 norm of sm minus sn.
So in
When
this case, since the basis is only one phi of t,
yes,
it will be one
it's one
dimensional, right?
dimensional basis. It's
Yeah.
one dimensional basis. Or as I said earlier, you can represent all the signals as points on as multiples of a single line. So that's why this is a one dimensional basis.
Okay, but we represent it on a paper, so we are calling it 2D representation.
Yeah, we
Okay.
because next lecture we'll be dealing with 2D cases.
Okay.
Okay, and and the minimum distance between 2 points is important. So I'll just finish off with this. So the minimum distance between 2 points on a signal constellation is important and is denoted Tmin. And in this case, you can see that for this case, d min equals right.
Yeah.
Yeah. So we should stop here. Yeah, we will stop here. So I was able to, despite the malfunctioning laptop, we were able to finish one lecture worth of notes today, which is a good thing.
Sir,
So yeah,
sir, slightly off topic. Is the scorpion also visible? It should be following the Orion, I believe.
see, I these days it's foggy, you know that.
Yeah.
Yeah, so the I and honestly, I haven't been on the roof since when? Since maybe September.
Okay.
I haven't climbed up my building's roof since September, so I don't know. That would be the honest answer. But in June or July, whenever I last looked, Orion was visible.
Okay.
Orion was clearly visible. I couldn't recognize anything else.
Yeah.
Okay, so let us stop here and continue on Tuesday.
Thank
Bye.
you, sir.
Thank you, sir. Thank you, sir.
Thank